All right, there's one more thing we can learn using the ideal gas law. I mean, there's more than one thing, but one more thing we're going to learn. And the ideal gas law can be used to prove Dalton's law on partial pressures. So we can find partial pressures of unreacting gases. So this is not like stoichiometry. These are molecules in the air that don't react, or in whatever your container is, that don't react together. Now, a couple of things we know are that ideal gases form are homogeneous. So in the room I'm standing in, there's oxygen and nitrogen and carbon dioxide. There's hydrogen. Oh, let me see. What else might there be? Oh, yeah. Now, those are non-reacting typically, but right now this building is being converted. They're doing some kind of tile work, and it smells like paint thinner. Okay, so those are molecules in the air, so whatever that ethanol or acetone type of substance is. But they may be reactive, but there's still some in the air. Okay, so we have learned that gases are miscible. All right, they mix together easily. And even though we don't really think of it that way, gases are also considered solutions. Now, the reason that this will work for us is because each ideal gas in this room or in whatever container acts like it's the only thing in the container. Okay, so it has some amount of pressure. It doesn't matter what the rest of them are. The pressure of one gas contributes whatever its amount is to the total pressure of the gas. Now, this was figured out by a man named Dalton, okay, Dalton's law of partial pressure, where he said that each gas, well, what he did was he did a bunch of experiments where he did things like he would gather insoluble gases, and then he would measure the pressure. And he did that over water. And the pressure of the water always contributed something to the total pressure of the gas. All right, so he figured out that the total pressure is the pressure of gas 1 plus 2 plus however many more there are. And in this case, he said, well, you know, the pressure of whatever of 1 is equal to the moles of 1 times RT in volume. Well, RT in volume don't change in any given place. Only the amount changes. So he said, well, we can add all these amounts together and we can figure out what the total pressure is. Okay? So only thing we have to do is add total pressures together. Well, that's not the only thing, of course. But we add those total pressures together and we get the overall pressure of the room. Now, another thing that we can use this for is to find the mole fraction. All right, so if we know the total pressure, okay, if we know the total pressure and how much of a certain amount of gas is in there, we can figure out the amount of that gas. All right. Now, another thing we know, this is called a chi, this x, which is, I guess I didn't really get a good one, but anyway, the chi is called the mole fraction. We use that to find some partial pressure. Okay, we know the total pressure, but we can figure out what the partial pressure is once we know this mole fraction. So when we add up gas 1 plus gas 2 plus gas 3 plus gas Z, or however many, all that's going to be equal to 1, okay, 1. Because that's all there is in the room, it's equal to 1. But we can add all these together in fractions, you get a value of 1. And so here's a little bit about this collecting gas over water, which is how Dalton figured these things out. And so in this case, he took some metal. Okay, we're going to do a problem in a minute where we take metal and react it. And the gas that's produced is H2. Well, H2 is bubbled through this water. but it doesn't dissolve into the water, so it actually collects in this tube that we caught. Well, because there's water in this that it's bubbling through, some amount of that water is also contributing to that pressure. So our total pressure here in this particular case would be the hydrogen plus the pressure of the H2O. Well, we probably don't care much about the pressure of the H2O if we're doing some experiments. So to find the pressure of the H2, we take the total pressure and we subtract the pressure of the H2O. Now, where do you get pressures of the H2O? It's totally dependent on the temperature. Totally dependent on the temperature. And you can get that out of a table in your book, all right? And we'll do a problem on this in a minute. All right, so a couple of problems here. We've got a closed system, 725 mils. It contains some neon and some argon. Okay, so those are unreacting. They're noble gases, and they're not going to react with each other. We know how much neon there is, but we don't know how much argon there is. However, we know the pressure and we know the temperature, so we can figure out how much or how many moles of argon there are. So let's get to the right problem. First thing we need to do is figure out what the total pressure is. All right, so we can find that because we have it. What am I saying? It's 1,000 inches of mercury, but this is going to be using the ideal gas law, so we need to convert this into atmospheres. So 1,000 inches of mercury times 2.54 centimeters divided by 1 inch times 10 millimeters for every 1 centimeter times 1 atmosphere over 760 millimeters of mercury. After I converted from inches, I got to millimeters. So inches are out, centimeters are out, millimeters are out, and I have atmospheres. And this works out to be equal to a whopping 33.4 atmospheres. 33.4 atmospheres. Okay, so a lot of pressure here. Now, because I know the pressure, okay, I've got the pressure, I've got the temperature, I've got the volume, I can find in total. In total. That's PV divided by RT using the ideal gas law. So we'll put in, I'll go ahead with that, 33.4 atmospheres. Will I be happy if you put in 0.725 liters instead of 725 mils? Yes, because our units are in liters. Got to have it in liters, atmospheres, and mole, and Kelvin. So I've got to have everything in the right unit. And in this case, 298 Kelvin. I already put it in there to make, a little less work for us. And we find out that N, the total N is going to be equal to 0.9897 moles. So how does that help us figure out how much argon there is? Well, we know enough information about the neon to figure out how many moles that is. So I guess I'll go up, even though I hate to do that. In this case, we have 2.35 grams of neon. So we can figure out how many moles that is by using the molar mass, and that's 1 mole over 39.95. No. How about 1 mole over 20.1618 grams of neon? And that tells me I have 0.116 moles of neon in this sample. So to find, remembering that N total, in this case, is going to be the N neon plus the N argon. That's going to be rearranged to help us find the amount of argon. So in this case, 0.9897 total minus 0.116. Do I have one more on there? Yeah, 5 for the neon. Tells me that the amount of gas in the sample is 0.873 moles of argon. 0.873 moles of argon. So what I did here is I took NT minus the moles of the neon, and that tells me the moles of the argon. All right, in this case, I've been told something about the mixture. I know how many grams of CO and SO2, or non-reacting gases, are in this case. And they have a pressure of 0.33 atmospheres together. Okay, so we know the total pressure here. Let me find my problem, what I do with it. Oh. All right. All right, so we have a pressure total of 0.33 atmospheres. Okay, so we're told these two unreacting gases together have this pressure. And we want to know what the partial pressure of the carbon monoxide is. So in order to figure that out, I need to know how many moles of everything there are. So I would go use 7.0 grams times 1 mole of CO divided by 28.01 grams of CO. And that tells me that 0.25 moles of CO are in that container. For the SO2, I have 10 grams SO2. I'll convert that to a mole as well. And well, that's 64.06 grams on the molar mass there. And this works out to be equal to 0.16 mole of the SO2. Okay, so now, using the equation where I know that PT is equal to the chi per CO times the total pressure total, that's going to give me the pressure of the CO. Okay, so I'm going to take the mole fraction and multiply it times the pressure and figure out what the pressure of CO2 is. But I need a total here. Our N total, add these two up, and this works out to be 0.41 moles total. Okay, we don't care about the individual right now, 0.41 moles total. Let's see, I wish I could not extend so far. But anyway, so here we are getting the pressure of the CO. We're going to take the N of CO divided by the N total times the total pressure to give us the partial pressure of CO. So this would be equal to 0.25 moles divided by the total moles, 0.41 moles, times the value given to you in the problem for the total pressure, 0.33 atmospheres. Okay, moles are going to drop out, and you're going to end up with units of pressure here, and it works out to be 0.20 atmospheres of pressure are exerted by that carbon monoxide. All right, so here is Dalton's law, where we're going to figure out how much the water the water volume is, and so we can figure out the total pressure of the H2. And so I'm going to take some zinc and hydrochloric acid, and one of the products is H2. So I'd say zinc, and in this case, this is aqueous. That's going to give me zinc Cl2 plus H2 gas. And this is aqueous as well. All right, so the only thing I'm collecting in terms of gas in this experiment is the hydrogen gas. But I'm doing it over water. Remember, we have a tube here. Some kind of reaction is going into it. It's sitting in water right there. Got some reaction happening, and it's collecting gas up here. And some of that gas is water, and some of that gas is hydrogen. So we've got a reaction at 16 degrees. And what else do we know? Gosh, we don't know anything. We should know that the total pressure is equal to 752 torr. And do we care outside of that what the volume is? Not particularly, okay? But we do need this temperature at 16 degrees, because when you look in the table in your book, table of pressure for H2O at 16 degrees Celsius, you'll find that that's equal to 13.6, torr, 13.6 torr. Okay, so usually these tables are in torrs. So to find the pressure of the H2, in this case, I'll take the total pressure, which is given to us in this problem, or no, it's not, but it's given to you now. The pressure of the H2 is equal to the total pressure minus the pressure of the H2O, which we get out of a table. All right, so this would be 752 torr minus 13.6 torr. And so in this case, this is 738.4 torr. Okay, so finding partial pressure when it's done over water is relatively easy because there's a table that tells you everything you need to know about the pressure of the water, as long as you know what the temperature is. Okay. So I guess we'll be moving along to our next lesson.